So, okay, I'll start. Welcome to this presentation. So here I'm going to cover this time the book Your Code as a Crime Scene. This has also been seen on my bookshelf for some time. So as let's say the too long didn't read is that basically with what this book offers or shows is that we can uncover problems and trends in our code base using simple metrics. Actually, the book offers a tool that I'll show in a moment that we can gather these metrics and then elaborate on them. It offers different concepts. Such as hotspots, so that once we identify hotspots, we can use them to drive development effort. I'll give some examples on that. We can also use this metric to identify coupling, so coupling between different pieces of our code base. That can work either for modules, let's say for classes or functions or files, let's say, or even extend it to architecture. And we also see code churn, that is a way to track code evolution. Finally, the last section of the book talks about social biases and why they are important. So let's say the first section is evolving software, and it presents this idea that in order to successfully maintain a code base, we must try as hard as possible to lower its complexity. So the idea is that we as human beings, we have a limited amount of cognitive power. We cannot have a big code base wrapped around our heads. So the goal is that we use tools to help us reason about a code base. And in this case, what we can do is we can use these metrics to know where to start, what to prioritize when we have to improve, and think about, let's say, the return of investment that we achieve with those improvements. One of the things that the book goes and offers in different steps is this idea that we can we can use forensic psychology as an analogy to think about the code. And one of the things that it says is that, for example, serial killers, there is a branch of forensic psychology that uses geographical profiling. So that means that they put different spots where on a map where crime occurred, and they try to see if it's located in a place to help track the killer. Now, this geographical profiling detects hotspots in a map, and what we are going to do is we use our version control. So in most cases, our Git history to derive this geographical information and to find the hotspots. And as I mentioned, let's say we use these hotspots to drive our development. The book what mentions is that whenever we are considering the information, we say that a hotspot is a combination of complexity and effort put into a module or put into, let's say, a class. And let's say for the book, complexity is measured in lines of code, and effort is measured in how frequent that piece of code changed. There is a caveat there that he mentions is that let's say measuring complexity by lines of code maybe a bit simplistic, and intuitively one could think, hey, there is nothing wrong with a file that has too many lines of code. He goes into the research and he mentions that although there are different ways of measure complexity, lines of code is the simplest, and apparently there is not a clear winner between these different ways of measuring complexity. Maybe we can think about cyclomatic complexity, and that won't trump over lines of code. The book introduces this tool called CodeMath that you can find in GitHub. You can find different examples, and that, let's say, exports data from your version control into some CSV file. There are different kinds of analysis that go over the book that we perform over the same information, and then from that we can derive it. So, as an example, this is how geographic profiling looks like. So we see different, let's say, events that occur in a map, and we can see that 2, 8, and 6, they are closely related or located, and that's what a hotspot would be, right? Like that's the idea of the hotspot. The book also mentions Code City. So Code City is also an open source tool that I couldn't make run. I think it's because I have anyway. But I think it would be possible on Windows. This is, for example, the code base of JDK 5 turned into a city. So different blocks refers to different packages, and the height of the building refers to the amount of lines that there are in that package. So there's like different, I think different buildings are different classes. So, and then if you see the blue underline, so that's the package. So this is another way to visualize complexity in a code base. And for example, this is the a diagram of the complexity of CodeMath itself. So the author goes over the different examples and different analysis, and he takes a look at his own project, takes a look at Hibernate, takes a look at Minecraft server written on .NET. And yeah, this is, for example, the same thing that we would see in Code Cities, but let's say in something, let's say, two-dimensional. So, as I mentioned, we can use get to track this spatial movement and use lines of code as a proxy for complexity. But let's say how we perform the analysis can be a bit tricky, because what we do is we have to select a time range where we have to do some analysis. So maybe if we select over some months, we will detect some hotspots, and if we do it in another time range, we will detect another. The idea is that over time, if everything goes well and some effort is put into lowering the complexity of code base, that hotspots cool down, so they are no longer flagged as hotspots. I find that a bit hard to believe. Like sometimes, let's say the complexity is there and we have reached that level of complexity, but at least and we decide not to touch that module anymore, and we just flag it as okay. This is it is what it is. But as I mentioned, what we can do with hotspots is that we can prioritize design issues. So if we take the different hotspots, we can say, okay, this is the one that contributes the most to the quality of our code base, and we work on that before. We can also perform code reviews, not code reviews in the sense that we create let's say we are reviewing someone else's code to merge a PR, but more like we are getting inside a project. This is the first couple of days that we're working on a new project. We can use these tools to identify which are the key players on the code base, and let's say maybe gain a better onboarding on the project. Also improve communication. So once we have detected hotspots and we have the data to show that, we can communicate with different members of the team and tell them, hey, we need to do this because of this is a hotspot, or we should do, and we can let's say guide the effort like that. And also narrow defects. So as I mentioned, this idea of having a code base too big is hard to understand. So by having some analysis done up front, we can narrow where defects are located. So this is the central idea of the book. We detect hotspots, or we do some kind of analysis, and from there we evaluate what to do next. Obviously, like one thing that derives from this is that this is not an absolute truth. Even, let's say, the metrics are simplistic on purpose, just because they are simpler to implement by, let's say, CodeMath, or let's say by also when we want to visualize the results. But it's kind of like, it's not an absolute truth. It's just some support tool that we want to use as a way to guide our design process. We still need to put our own expertise to decide what to do with that information. So as I mentioned, the way that we can choose these time spans, or these time ranges when we are doing analysis, is that we can select different releases. So let's say we check where are the hotspots between version 1 and version 2. Over iterations could be, let's say, between sprints and sprints. Like let's say we can see how the hotspots are evolving over the different sprints and how our code base is evolving. Or even also, let's say, around significant events, which could mean anything. Like, for example, recently Alberto dropped from the team, and that's a significant event. Like we can go and check an analysis on, let's say, his contributions, and let's say derive some information from that. Maybe before him leaving, we could detect something that we don't understand well enough, and we can go and ask him, hey, I don't understand this, can you explain it to me? Ideally, let's say these time spans shouldn't be too big, otherwise, let's say, some results could be skewed. That's also something that I'll mention at the end of the talk, when I show you a graph of one of our projects, that I had to kind of like check some of the data, because I was getting some spikes on the analysis, and that was because some invalid file was getting in the middle. And obviously, let's say what's interesting is that we can visualize hotspots. So I think that's a nice way to just point a finger at what's going on. I'm not sure if you can see this, but here we can see, let's say, this entity would be the hotspot, and that's the entity that we should consider. And then we have other modules that are not so much the problem. But at least, let's say, kind of like a picture says more than 1,000 words. This comes from the fact that, let's say, one of the things that the book does is CodeMath only parses text files and outputs CSV. So it's hard to understand, like, plain numbers and plain text. That's why it's usually easier to see it in a picture, and then dive deeper on the actual text. Once we have detected the hotspots, one thing that the book mentions is that we could face false positive, so something that's not actually a hotspot. And the heuristic that the author proposes is that we evaluate, or we quickly evaluate these hotspots based on the name of the module, to see if that's the case or not. So in this case, for example, goes over Hibernate and checks how many changes the module has how many revisions it has, and how many lines of code, and sorting this by let's say, by complexity. The first one would be the most complex, so it's build.gradle. It says, hey, it's a bit big, but let's say it's just configuration for the build, so we can ignore it. Then we have abstract entity persister. So since this is Hibernate, it may be central to the business case, or the business use case of Hibernate. So maybe it's not really a hotspot. It does mention that the fact that we are attaching prefixes or suffixes to a name could flag as something like a bad name. But then, for example, it turns and shows configuration. So usually configuration shouldn't be something that, let's say, why Hibernate needs to be configured with something that has 2,000 lines of code, more than 2,000 lines of code. So it goes and says, hey, maybe whenever you're considering a hotspot, try to see if it has a good name or a bad name to determine if it's a hotspot or not. Usually what the intuition that you get through the book is that whenever a class changes too often and thus becomes a hotspot, is because its responsibility is not clearly defined. So let's say its changes are occurring all the time because our understanding of the module is not clear enough that we can say, okay, this is its responsibility, the implementation is this, and it's done. No, we iterate over and over again, and the fact that maybe the intuition is that maybe if the name of the class is not properly set, it doesn't have a good name, then it could be because we don't understand its responsibility well enough, and thus we keep coming back to it over and over again. So usually it says that, let's say for good names should be descripted and declare intent, and should express only a single concept, such as, let's say, TCP listener, concurrent queue, and so on. And then that bad names carry little information and convey no hints to the purpose of the module. So something like state manager or helper or utils, something like that. Or classes that use conjunction, like and or. So let's say some connection and session pool. So that would be something that is probably mixing two responsibilities. So then it goes and says that complexity can also be calculated, or it can also be displayed as a graph. Like we can show the trend of a hotspot and see how it's evolving over time, if it's cooling down or if it's remaining hot. And one of the things that mentions is that another way to measure complexity is by using the indentation. He mentions that, let's say, indentation is a quick way to, let's say, go through the file and say, okay, if this file has too many indentation levels, that's because it's more complex than one that doesn't have. I think that this is kind of like, the book doesn't mention it, but it's kind of like a proxy for cyclomatic complexity, right? Like whenever we have too many branches, usually, let's say if we are doing Java, we tend to use curly braces, or even in Scala, we tend to use curly braces and nest our control flow or our code base. So yeah, it's mentioned that it's easier to calculate. Nonetheless, there are ways to quickly calculate cyclomatic complexity. So yeah, it's just one way to get the value. There is a tool that I think Jalal shared a few months ago called SCC that lets you gather information about your code base, and not only lines of code but also complexity. And I think that it also puts something like monetary, how expensive a piece of software is to develop. It also mentions something that we have to keep in mind, and this is one of Liemann's law of increasing complexity. That means that if as a program is evolving, its complexity is going to increase unless we do something about it. So that's something that we have to keep in mind. And then when we define that, or we find out that there's a trend in a hotspot that's going up, that's a warning sign that we have to take care of that. So for the first section, these are the key points. Basically, we can extract information from our version control to better understand our code base. So as I mentioned, a module or a class that changes frequently means that we haven't probably means that we haven't understand its responsibility properly, or let's say the design needs a bit of work. And yeah, that we can perform this analysis when we are just starting in a new project, try to understand it, or on a regular basis to find out problems. The only critique that I find on this section is that the tool only shows you CSV data, and the visualization is kind of like static. There are some Python scripts that show some PNGs, I think, or some static data that you cannot, from the CSV, derive some visualization. I'm not sure if this has to do with the fact that CodeMath evolved to be a paid product, so and thus, let's say, saving the best parts for people willing to pay. But nonetheless, there are some things that we can do out of the box, and that we can do with this data, like putting it on Google Sheets or something like that, and then plotting it. Okay, so the next section talks about architecture. So if in the first part we were talking about, let's say, individual components, here we consider packages, or we consider bigger groups of information. So in this section we move on to the second concept that I mentioned. So this idea of temporal coupling. So temporal coupling means that we can see that two modules or two classes change usually at the same time, like they change usually in the same commit. There are two types of couplings. So there are explicit and temporal coupling. Explicit coupling is when we explicitly decide that there is a coupling between two classes. So let's say one example would be a class and its test class. So every time we update that class, we maybe have to update its tests. Now, with temporal coupling, what we can detect is if, let's say, one class changes and another completely unrelated class change at the same time. What else? So yeah, some reasons of why this temporal coupling could happen is because we copy paste. So we copy paste a lot of code, and then we have to update whenever we have to update one of those versions of that paste, we have to update the others. Another could be that there is inadequate encapsulation, meaning that, let's say, we are leaking information or concerns from one class to the other. So something that we probably ought to fix. And producer consumers. So let's say when we have a producer that updates the way that some event is produced. Let's say that those producer consumers are decoupled on purpose, right? Like we are sending information through Kafka with a producer, and we are consuming it with some other module. The fact that these two have to change together means, well, because they are tied not directly through code, but more like one doesn't depend on the other by, I don't know, injection, but more like because, well, they are coupled that way. That doesn't necessarily means that it's a bad thing. Like maybe it's intended. It's just something to take into account. So one thing that it mentions is that temporal coupling is research shows that temporal coupling is directly linked with bugs, and the reasoning is that let's say this temporal coupling is coupling that we don't see in the code base, that we don't set explicitly. Could be because the design is incorrect, and the fact that it's temporal, or the fact that it's hidden, means that we cannot reason about. And maybe by modifying one piece of code, we forget, or we don't know that we have to modify that other implicit coupling, and we introduce a bug because we should have done updated both. Yeah, so again, once we have detected that there is some temporal coupling, this could also be a false positive, but it's kind of like a warning sign saying, hey, you need to go in and investigate what happens. Yeah, so just as, let's say, with hotspots, we can also track this over time and see if there is a negative trend to react upon. And yeah, that there are more than one way to detect temporal coupling. So in this case, the book only mentions coupling that happened within the same commit, but usually that's not how things work. Usually, let's say we do a commit, we change something, and then we realize that we have to fix it. We come back maybe a few commits later, and let's say the book doesn't take that into account. So it could be possible to, but it does mention it, that it could be possible to, let's say, extend how far away we take this into account. And it also, let's say, talks about another Lehman law to keep in mind, and is that so the law of continued change, saying that a product needs to evolve over time, needs to add more features in order to keep being useful, right? Let's say the goal of a product is to become useful, or otherwise users will move away to use another product. Now, obviously, there is a tension between the other law that talks about complexity, right? Because it says that, so this law says that a product needs to change all the time, and the other says that if a product changes all the time, its complexity will increase. So we have to kind of like keep those things in mind, keep those things in check, trying to change things to be so that the product still is useful, but not so much or in a careless way that it becomes a mess that will make the adding features to the product harder because of bugs. For example, one thing that starts to mention this idea is that, let's say, usually an architecture is a set of principles and rules. It's not necessarily only something that we see on a diagram or like a UML diagram. That's not the only way to represent architecture, at least not in our heads. So let's say whenever we are selecting like MVC or I think pipes, these are different ways to reason about how we introduce things to our code base. And once we have that in mind, what we can do is we can introduce boundaries. We can define boundaries as, okay, these are the models, these are the views, these are the controllers. And the tool, this code mat, allows us to say these files belong to this boundary. Let's say all the classes that are located in the package, in the view package, are related to our views. All the classes that are in the controller package are controllers, and all the all the ones that are on services are, well, services and so on. For example, let's say before jumping into more complicated examples, the book mentions that we can treat our tests as another boundary. So we have, let's say, source main as our application code, and then source test as our test code. And we can see how concerns are leaking, or if concerns are leaking, or if there is a temporal coupling between these two boundaries, to show, for example, if let's say if we are spending too much time working on the test, we are adding more lines to the test than lines that we are adding to the application code. That could mean that we are spending too much time on the tests and not enough time on the application code. And the idea is that users are going to use the application code, not the test code, meaning that we could be spending too much time in something that, well, let's say, doesn't benefit users, doesn't add value to its users. And if we spend too much time there, and then, as well, we can, as I mentioned, we can perform trend analysis over that ratio. It also mentions that we can use beauty as a guiding principle, but beauty is basically consistency. The idea is that we can, if we have the rules or the principles of our architecture clear enough, we must be as consistent as possible, so us and other developers doesn't face surprises when they are inspecting our code base. Let's say the fact that there are surprises or there are changes inside the architecture means that someone has to think about those exceptions and keep those exceptions in mind, meaning that there is a bigger cognitive overload on the or overhead in the developer when they have to do the change. So, for example, one thing that it mentions is that again with MVC says that, for example, you may have to change a model inside an application, and by changing the model, you have to update the view, you have to update the controller, you have to maybe update the services, and that shows kind of like this idea that maybe that's not a good architecture, because you have to change multiple modules at the same time, or multiple boundaries at the same time. I'm not entirely sure if I agree with that. Like, let's say it's a nice way to think about an application, how to structure an application, and it's not like, so if models are supposed to change, maybe something has to be translated, or that change has to ripple through multiple pieces, but that doesn't mean that every change will have to be done that way. Sometimes we just update something in the persistent module, and that doesn't ripple through. If the application is well designed, that doesn't ripple to the other places. One thing that I feel this idea of architecture fails here on the book, although the book mentions microservices, I'm not sure if it's clearly understood how this will be implemented. So the tools that we have are related, can only dig information out of a single repository. But as soon as we have more than one repository, that falls on its face, because there is no way to correlate information. Nonetheless, I think that there is still hope. There is a way or there could be a way to correlate that information that I'll mention at the end. So yeah, these are the key points. So we talk about temporal coupling, how we use it to detect hidden dependencies, sorry. And yeah, so even if we get a lot of data and a lot of numbers here and there, we still have to, again, come up with this judgment ourselves. We have to inspect the information and derive information from that, like meaningful information. And the same as before, I think that more visualization tools out of the box would be great. Like if you can not only output CSV, but represent that with the examples that they are seeing, and try it for yourself, that would be way easier to digest. And the final section talks about, let's say, the social aspects of code, meaning that, let's say, programming is a social activity. So, right, we have to communicate with customers, with peers, with managers. And one thing that we face with this is that this concept of process loss, and is the fact that by working together, there is an overhead that each one of us have to pay to that we drop in our performance. So our performance is not 100% as we would do as individuals. And let's say we could think about this like, let's say, some communication overhead. The fact that, let's say, maybe we have to have a meeting, and that meeting is a waste of time, or mostly a waste of time, but we need to have that meeting to sync with each other. So let's say the output that we can deliver as individuals suffers. Nonetheless, this is accepted. So we work in teams as a way to achieve a bigger goal, right? Like there is this phrase that says, if you want to go fast, go alone. If you want to go far, go together. And I think that this is what it means. Now, one thing that the book emphasized, and I think is pretty interesting, is the idea of biases. So I'm not sure if any one of you read Thinking Fast and Slow. Sorry, Thinking Fast and Slow. So that talks a lot about biases. It's not a coding book or a programming book, but it's closely related to what we see across the book, and it's quite interesting. That would be a nice book to read. But one thing that mentions is this idea of pluralistic ignorance. So once we start working in a team, and that team is, let's say, defines a status quo, we tend to conform to a norm, and maybe sometimes some things that could be improved are not spoken out loud. That's one of the reasons why I think that getting new team members into a team is super interesting, because they can see things from an outsider's perspective and point out, hey, maybe we should try this, maybe we should try it out. Let's say, well, obviously team members should be open to that experience. Nonetheless, if that doesn't happen, what the book mentions is that we can fight this pluralistic ignorance or this status quo with questions and data. So we can go and ask questions to individual people, how they feel about a particular decision, what they like and what they don't like. Usually they should be, sometimes it's difficult to ask that question because people are afraid of getting some criticism, but doesn't hurt to check. And also kind of like support the decisions with data. So if the idea of this book is that we gather data from different places, and with that we can base our analysis. So one thing that this chapter mentions is this idea of commit clouds as a way to start discussions about what's going on in a code base. So in this case, commit cloud is taking all the words that are on a code base in the commit messages and seeing what words are the most frequent ones. So this is one of our projects. I took all the commits. I removed Scala Steward because it was it was everywhere, and then I left the most important pieces of information. So the idea here is that we can look at a glance what's the word that has the most is mostly represented in our code base, and see if something is wrong. For example, one of the things that mentions is that we want to see words that are related to the domain and not, let's say, bad words, so to speak, such as fix or maybe test, and we should see something like add or update or something like that. Like say, having fixes is not a good idea, because, well, that means that we have to we have bugs. I think that I was talking with Jalal. He did a commit cloud, and his third or fourth word was fixed, but he deleted it because he didn't want it in the commit cloud. Yes.
Should we remove also words from the conventional commit template?
Yeah, that's a good point. Yeah. So in the project we use conventional commits, so we prefix the commit message with either if it's a feature, if it's a fix, or if it's a bug. Actually, we can skip it, or we can also, let's say, only keep that one, and then we can probably do a distribution and say how many features are we rolling out against how many fixes or how many chores. So that's another way to, let's say, to roll out the information. Then what it mentions is that we can also have this idea of deriving information or code quality from a team's perspective. Usually, what that means is that we can identify who are the responsibles for a piece of code, and then see if they are working close to each other. So the chapter starts with, let's say, with Brooks' law, that basically says that a woman can have a baby in 9 months, but 9 women cannot have a baby in a month. So this idea that adding manpower to a late project will only make it later. And also that, let's say, defects are usually are more prone of when people are working together. And he mentions, I think, Windows Vista as one of as a piece of research that came and say, hey, this piece of software failed because too many people were working on the same piece of code, and that introduced a lot of conflicts. You can probably think about the last time you had to do a tricky merge conflict, so that you had to step in and make sure that your code was still working and this other person's code was still working, and that sometimes is hard to understand. So usually, let's say, from time to time, we we try to work as a team in a way that we avoid or work around those issues. So if we know that 2 tickets are going to work on the same sprint on the same piece of code, we say, hey, maybe you can wait a bit, let me finish, and then we can go back and see. Because also on the merge conflict, usually it's hard to understand and to reason when you are trying to fix it. And also this idea of diffusion of responsibility. So meaning that the fact that we're working on a team usually prevents us from knowing who's responsible for what. It goes and explains this with an example that a woman was screaming in the middle of the night and no one called 911. Why? Because everyone thought that someone else already called. So this is this idea that yeah, we have to keep that bias in mind. Recently I heard someone talking about I'll explain later. That's okay. And also, then again, something that mentions is that it mentions Conway's law, in the sense that when an organization designs a system that could be a product, eventually that system, that the design of that system will reflect the communication structure of that organization. So one thing interesting that mentions here is that, well, maybe we can, if we have an ideal architecture and we start modifying that ideal architecture because it has to resemble our organization, the book mentions that we can put a spin on that, and maybe we can think about this. Maybe we can think about the ideal architecture, and once we have the ideal architecture, we modify the organization or the communication structure as a way to support the architecture of that application in a sense that, let's say, keeping in mind that it will happen nonetheless. So the idea is that to think, for example, if developers are working close to each other, and optimize communication if they are not. So in a nutshell, it looks like this. So we first identify parallel work. We compare that parallel work against hotspots. We identify temporal coupling. We find the main developers of those hotspots and or the classes on those hotspots and the classes that are related to the hotspots. Then we check the organization distance, right? We check if these people are working close to each other, and if they are not, we try to put them on the same team. Also, another thing that we could think of is, let's say maybe they are working on the same team, but they are working on different time zones, or they are working remotely, and optimizing for communication would be something that could improve this parallel work. Then, well, also mention something that is related to that preface, and is this idea of ownership models. So the idea is that we can from a piece of code we can detect who made the most commits or the more contributions or knows the code the most, and the fact is that the fewer owners with a piece of code means fewer defects and simpler communication. I think that this is sort of true, not necessarily, like because let's say fewer defects, that depends a bit on the person, and also we still want to work together. We don't want to have a low bus track factor. So if one person knows a critical piece of information about a code and that person is gone, then yeah, we're in trouble. So fewer doesn't necessarily mean one. Then what we can do is we can, let's say, extend over architecture, and we can also visualize with this ownership what would happen if someone would leave the team. Let's say we can know, okay, for these modules, if this person would leave, someone else will need to take over. So would also serve as a way of seeing how, when someone offboards the team, what do we need to put emphasis on. And this is something like something that we can see, and the book mentions that we can define some. This is on Hibernate, and shows for different classes like entity persister or goofy persister class provider, which are different maintainers. So each square is one maintainer, and well, here's the legend with the codes. And it mentions that, for example, if the square has only one color, that means that it's a single developer. If it has more than one color, but we have fewer contributors that have a bigger footprint on the diagram, that means that the class is healthy, right? Like, because all the knowledge of the code is concentrated in a few developers instead of on different ones. And this would be the worst case scenario where we have multiple people owning different pieces of the code, and meaning that or hinting that maybe the knowledge about the code is fragmented across different developers. Finally, what mentions is this idea of code churn. So code churn is another metric that we can use to measure the rate of change of a code or of a module, and it allows us to predict defects and unstable features. So ideally, as I mentioned, let's say with the complexity or with the complexity, that we could plot it in a graph and see through revisions if it was stabilizing or it was increasing. The idea is that the amount of changes that we do should stabilize in some moment. We shouldn't keep adding to a class, so at some moment that class needs to stop being modified because of the thing that I mentioned before, this idea of responsibilities. Usually whenever we plot it in a graph, we should see a small stream of small commits, a state stream. That means that it's healthy, like we are doing some iterative work over that. But if we have spikes or weird trends, that's when we need to we need to investigate. We can also, let's say, combine this information with other metrics. So we could use this with temporal coupling and then see what to improve first, like a code that is a module that is changing too fast and also has temporal coupling with another class or with other classes. We can go in and refactor those first, and we can also detect hotspots with this. So before, as I mentioned, we detected hotspots by combining the complexity, so the lines of code, and the effort, the amount of revisions that a class or a module had. In this case, we can combine the complexity metric, whatever that is, let's say lines of code, and the code churn to replacing effort to identify hotspots, and then we can probably cross-reference information. We can do more complex things. Now, there are some limitations on the information that we get from this. So we can get false positives with generated code or test data. Sometimes we change test data too often, maybe. The easy fix for this is just to filter it out of the data analysis. Some refactoring, right? So if we do big bang refactoring or big bang refactors, then that would show us a spike, and we would have to flag that change out, or some superficial changes. So the book what mentions is that maybe adding a single modifying the name of a variable has roughly the same impact as, I don't know, something a bit more complex that is also one single line. So maybe it's, we will get some big spikes, but that doesn't mean that it's a big problem. So, for example, this is I grabbed the project and I ran it through code churn, and then I plotted this. And let's say this red line means that at some moment we deleted a lot of lines. So when I went in, I tried to inspect this. This was some JSON file that we were using for test data to push to the test client, and we deleted it and we generated it somehow. So we had to go in and inspect, hey, why do we have this data? Okay, we have to remove it from the analysis. But otherwise, you can see that we have I wouldn't call it spikes, but we have some information that goes over. And then, finally, what it mentions is that, well, this is only a starting point. We can roll out our own tools. We can roll out our own analysis. And the suggestion that the author has is that we should start simple. Like, one of the things that I mentioned is that lines of code may not be the best way to measure complexity, but it's a very simple metric to calculate. And that we should follow the same approach and only add more complexity to our tools, to our analysis when it's needed. And let's say, then also mentions some other approaches, right? So one thing that I mentioned is that we cannot cross-reference this information across different repositories. We could take this analysis beyond the code itself. We could also take in, let's say, do some analysis in our Confluence pages, in our wiki pages. We can have all other kind of information. So, for example, in our project, we tag the tickets. We tag the commits with the tickets. So theoretically, we could ingest the information from our different systems and then correlate the different commits by that ticket number. So that would be one solution whenever we have a microservice architecture that is propagated across different repositories, as a way to tie in those commits again. And also, well, it mentions Moose. Moose is an analysis tool, an open source analysis tool that we can apparently add plugins to it, and we can add our analysis, our own analysis. So yeah, that's it. Thank you for listening.